All right, good morning. Uh, this morning, I'm going to be repeating the class we had yesterday. Uh, the reason because of picture quality. So as a result, I'm going to be taking this uh, topic again, electric field. So this morning, I'm still going to be summarizing it just in few steps. Remember, as I said yesterday, this particular topic is for students in SS3 that are writing their WAEC exam, NECO, NAPTEP, and then JAM, and also for undergraduate students in year one at the university. Okay, so we'll start by defining field. We say field is a region or a space around a source where the influence of the source can be felt. Or you can say that field is a region or space under the influence of some physical agency, such as electric field, magnetic field, gravitational field. And then I said when you talk about magnetic field, you are talking about field around a magnet. When you talk about gravitational field, you are talking about field around a mass. And when you talk about electric field, you are talking about field around a charge. These are the three major fields that we have. Yes, we have other fields, but these are the three major that we study in physics. Okay, so we are going to take electric field this morning. And electric field says is defined as a region or space around a charge where the influence of the charge can be felt. It is a region or space around a charge where the influence of the charge can be felt. Okay, now let's talk about the types of charges that exist in this electrostatic field or electric field. Now we have two types of charges. We have one, positive charge, and then we have negative charge. Negative charge. Okay, so these are the two types of charges that exist in electric field. All right, now for positive charge, if you have a positive charge, the field is radially outward. This is the direction of field of a positive charge. If you have a negative charge, the field is inward. The field is inward. And so therefore, this follows the law of electric lines of force, that the charge begins from positive and ends in negative. The line of force begins from positive and ends in negative, okay? Now, there are two types of forces that exist in electric field. We have repulsive force and attractive force. And that takes us to another law of electric lines of force. It says like charges will repel, unlike charges will attract. Like charges will repel. So if we have positive, they will repel each other. If you have negative, they will repel each other. But if you have positive and negative, force of attraction will occur. All right? So let's represent that diagrammatically. So if I have a positive charge here, I have a negative charge here. The field will move from positive and enter negative. It goes out from positive and goes into negative. All right, so you can see that the field starts from positive and ends in negative. And another law says that the line of force do not cross each other. The line of force do not cross each other. So that is it. Then if we have maybe like charges, let's say positive, we have positive, the field will be in this form. the field will be in this form. This point is called null point, and this is where the force of repulsion will take place. So this is where repulsion will take place. A null point, nothing is happening there. Because of this force of repulsion, the charges are repelling away each other. Okay, while here, attraction is happening. Attraction. There is force of attraction here, and there is force of repulsion here. All right, now, having said that, these lines you see here are called lines of force. These lines here are called lines of force. And what is this line of force? We say line of force is an imaginary line drawn in an electric field in such a way that its direction at any point indicate the direction of the field at that point. Okay? The lines of force is an imaginary line. It means it is a line, something that we cannot see, but we know it is existing there because it can act. It can act, so we know it is existing even though we cannot see it. Okay, so that is what we call lines of force. Now, having discussed that, we are now going to move into what we call Coulomb's law. The man called Charles Coulomb did some work in this electric field and told us that there is a relationship between force of attraction or repulsion between two charges, the product of the charges, and their distance apart. What did he tell us? So I'm going to summarize that law mathematically. Coulomb's law. So he says that the force of attraction or repulsion is highly proportional to the product of the charges Q1, Q2, and it is inversely proportional to the square of their distance of separation. I'll call that 2. If I combine this equation 1 and 2, I'm going to have that F is directly proportional to Q1, Q2 all over R square. I'll call that equation 3. Okay? Now, I can remove sign of proportionality so that we can have that F equal to a constant Q1, Q2 all over R square. And this is equation 4. All right, now this constant has a value, and this constant K is also given by 1 all over 4 pi epsilon naught. 4 pi epsilon naught, and this is equal to 9.0 as 10 raised to power 9 Newton meter square per Coulomb square. Okay, where this epsilon is called permittivity of free space. Permittivity of free space. Okay, now that is a Coulomb's law. That is Coulomb's law. Now this equation can as well be written as this, that F is equal to, since we have said that K is equal to this, we can substitute that value in that equation 4 so that we can have that F equals to Q1, Q2 all over 4 pi epsilon naught R square. So I can call this equation 5. All right? So this is the force of attraction or repulsion between two charges, equation 4 and equation 5. Okay, having discussed this, we can move into what we call electric field intensity or strength. Electric field intensity or strength. So we use E to represent electric field intensity. Now, what is electric field intensity? Electric field intensity is the force per unit charge at a particular point. The force per unit charge at a point is defined as electric field intensity or electric field strength. Okay? Now, let me use diagram to demonstrate that. We have what we call a point charge, and then the direction of this electric field intensity is here. Let's assume there is a test charge here, and this is a point charge. Okay? At this point A, we have a test charge. Now, what we call electric field intensity is the intensity of the force that this point charge is exerting on this test charge. That is what we are talking about. That is what we are calculating. The intensity of the force of this point charge on this test charge is what we call electric field intensity. Now, what is a test charge? A test charge is a charge that is so small that it does not significantly alter the field it is testing. A test charge is a charge that is so small that it does not significantly alter the field it is testing. Okay, when we start doing calculation, you will find out that when you compare the test charge with the point charge, you'll find out that the test charge is actually very small. Okay, now the point charge is the main charge, while the test charge is the charge that is used to test the intensity of the force of this point charge at all these points along the electric line of force. Okay, now having defined that, we said that electric field intensity E is equal to force per unit charge. Force per unit charge. And since F is in Newton, Q is in Coulomb, the unit becomes Newton per Coulomb. Okay? So we progress that from there. We can call this equation 6. If that is the case, we already know that F equals this. And since the relationship between E, F, and Q is this, we can rewrite this equation so that we have anywhere we see F, we can remove F and put the value of F, which is this. So we now have 1 over Q multiplied by Q1, Q2, all over 4 pi epsilon naught R square. Okay? Now, permit me, there's something I'm going to do here. I'm going to transform that equation. I'm going to transform this equation to this. So that I'm going to have that E is equal to 1 over Q multiplied by, instead of having small letter q, I'll have big letter Q over QQ over 4 pi epsilon naught R square. Why? Because we are talking about a point charge and a test charge. Okay? We are talking about a point charge and a test charge. So that is why, so that this will represent the point charge and this will represent the test charge. So this equation finally becomes, this will cancel this. We are left with capital Q all over 4 pi epsilon naught R square. So our electric field intensity is equal to Q all over 4 pi epsilon naught R square. So I can call this equation 7. So this equation 7 and the equation 6 becomes the formula for electric field intensity, and the unit still remains Newton per Coulomb. Okay? There are other units. As we progress, we are going to see it. So having defined electric field intensity, we keep that aside. We go to electric field potential, electric potential and potential difference. Electric potential and potential difference. And potential difference. So we use V to represent potential difference. We use V to represent potential difference. Lest I forget, Electric field is a vector field. Electric field strength or electric field intensity is a vector field. Also, electric field is a vector field. But for electric potential and potential difference, they are all scalar quantity. This one is a vector quantity, sorry. I mean to say that electric field intensity is a vector quantity. Yes, a vector field. Why this one is a scalar quantity? Yes, it's a scalar, but both electric potential and potential difference. They are both scalar what? Quantity. All right. So before I define electric potential and potential difference, I would like to use a diagram to, to define that so that you'll understand the difference between electric potential and potential difference. Okay? So if we have a point charge at this point, and this is the field of this point charge, we have 2 points. Let's call this A and let's call this B. Okay? Now, and the distance between them is R. Now, let me define electric potential. Electric potential is the work done in bringing a unit positive charge from a point at infinity or from a point at zero potential to that point against the electric force of the field. This is this field, this charge is exerting force along this area. So all this area are region of this charge. So it has influence around all this area. So we say when we bring a charge from a distance that is infinite against the electric force of this field, we say we have done work. And that is what we call electric potential. We say it is a work done in bringing a unit positive charge from a point at arbitrary zero potential or from a point at infinity to that point against the electric force of the field. So that is what we call electric potential. Let's assume we brought that charge and drop it at this point B. Okay? We drop it at this point B. Now, potential difference now becomes the work done in moving that charge from point B to point A in an electric field. The work done in moving that charge from this point B to point A now becomes the potential difference. So that is the difference between these two potential is what we call potential difference. Okay, now at this point A, the potential at this point A is higher than the potential at the point B. Okay, when we bring our cells have different potential. We have the positive terminal and the negative terminal. The positive terminal is the point that is closer to the charge, while the negative terminal is the point that is further away. So the positive terminal is at positive potential, while the negative terminal of a cell is at negative potential. Okay, it's at lower potential. The positive terminal is at higher potential, while the negative terminal is at lower potential. Okay, so having defined that, we now say that the work done, we said it is a work done in moving a unit positive charge from point, say A to point, say B. That is why when we define potential difference, we put V subscript AB. That AB meaning from A to B. Okay, so the work done here is given by W equal to QV. W equals to QV. That is work done equals to charge times potential difference, or electric times the electric potential. If we make electric potential subject of formula, we can call this equation 8. If we make electric potential subject of formula, we are going to have that V is equal to work done over charge. And this is going to be equation, let's call this one A, equation 8B. This is equation 8B. Now, both electric potential and potential difference are measured in volts. That is, their unit is what? Volts. All right. Why work done is joule. The unit of work done is joule. All right, so let's continue from here and derive our formula for electric potential. Also, there is a relationship between electric potential, electric field intensity or strength, and the distance between the charges. And that relationship is given by electric field strength is equal to V over D. You can call this equation 9, okay? Where V is in meter and D is in, where V is in volt and D is in meter, the unit here, the unit here is volt per meter. So the unit of electric field strength here is also volt per meter. So you can see that we have been able to derive up to 3 units for electric field strength. Okay, if that is the case, we are going to substitute this equation into this. Since E equals to this and E is also equal to this. So we can now say, making V subject of formula so that V becomes equal to ED. Then we substitute the value of E. Anywhere we see E, we carry this value and put for E. So that we are going to have Q all over 4 pi epsilon naught R square times D. Now, there's something I'm going to do here. I'm going to change this R into D because we are talking about distance between 2 points now. So that this equation now becomes V equal to Q all over 4 pi epsilon naught D square times D. This square will cancel this D, so that we are left with V is equal to Q all over 4 pi epsilon naught D. So I can call this equation 10. So this is the formula for electric potential. This is the formula for electric potential. And as I told you earlier, electric potential is measured in volts. So we have been able to summarize the whole of electric field in just few steps. All right. So in our next lesson, I'm going to be using past question, JAMB, WAEC, past question to solve some problems that will be requiring us to use all these formulas we have derived today. About 10 formulas we have been able to derive today. So we are going to solve past questions using these formulas, okay? So thank you so much. Please like, comment, and share. Also, you can join our YouTube channel for more lessons at perfect_tutors and perfect tutors at perfect tutors. In our YouTube, search for us, you are going to see us there, perfect tutors. So you comment, like, and also share. God bless you as you do that.